Hello everyone, myself Dr. Jayeeta Majumdar, Associate Professor of Department of Computer Science and Engineering of Haldi Institute of Technology. Today I am telling you through these slides one of the most important topic from the computer architecture, that is pipeline, and its introduction, its classification, what are the different activities, what are the different parameters of pipeline. This is. So let's start. Before going to pipelining, first we study what is parallel processing. Before parallel processing, now question comes, what is serial processing then? Serial processing is when number of jobs are there in the queue and one by one it is entered into the processor, and the processor, depending on the instruction, it process and release the output, and the next instruction comes to the, or next process comes to the processor. So one by one the processor process the data and produce the output. Now what is the drawbacks of serial processing? When more than one data, that is huge number of data, is in the ready queue for the processing, then the throughput is reduced. So to overcome these situations, the parallel processing concept is come. So parallel processing can be described as a class of techniques which enables the system to achieve simultaneous data processing tasks to increase the computational speed of a computer system. What I tell you? That is to achieve simultaneous data processing. That is, if more than one data is present there, that is, but suppose there are 10,000 data is there for processing. So how you increase your computational speed of your system? Then this technique is introduced, that is the parallel processing. A parallel processing system can carry out simultaneous data processing to achieve faster execution time. Faster execution time, that is to achieve the output or to get the output from the system, the parallel processing system is required. For instance, while an instruction is being processed in the ALU component of the CPU, the next instruction can be read from the memory. That means if here two resources used, one is ALU, one is in the CPU, and another instruction read from the data, that is the memory operation. One is the processor operation, one is the memory operation. So two instruction runs at a single instance of time. One is use the CPU, the ALU, for arithmetical or logical operation, anything, and another instruction, what is required, the data, it is read from the memory. So two operation is simultaneously running. The primary purpose of parallel processing is to enhance the computer processing capability and increase its throughput. So primary purpose, what is? To enhance the processing capability and increase the throughput, the amount of processing that can be accomplished during a given interval of time. A parallel processing system can be achieved by having a multiplicity of functional units that perform identical or different operations. This is the most important. So it can be achieved. How it can be achieved? How parallel processing system achieved this increase the throughput? Here in our system there are different functional units. So if we increase or increase the number of functional units, suppose there are adder unit, if there is one adder unit, so you can perform only one addition per operation in a single instance. But if you increase number of adders, means suppose there are 10 adders, so then 10 addition operation performs in a single instance of time. So that their data can be distributed among various multiple function units. So suppose one operation is A plus B, one operation is C plus D, one operation A plus C, in this way. So there are different data, and different data operates on different functional unit and produce the output. In the next slide there is a diagram how you use the different functional unit and working as a parallel. So you check in the diagram, suppose the processor registers are there which is connected by different functional unit. The first one is adder subtractor unit, then integer multiplier, then logic unit, shifter unit, incrementer, floating point and addition subtraction, floating point multiplication unit, floating point division unit. So there are all are connected to the processor register in parallel manner. You check the diagram, that is, this is the processor register which is a single line. Suppose it needs the data sent to the different unit, as well as the unit also sends the data to the processor register. So both way communication. So processor register sends the data to the unit, that is the adder and integer may perform the arithmetic operation with the integer. So adder, subtractor, integer may all are the integer numbers. Similarly, different floating point operations, it is addition, subtraction, multiplication, division, and logic, shifting, inking can be performed on a logical operations with different data. So all the units are independent. This is very much important. All units are independent of each other. So one number can be shifted while another number is being incremented. Okay. So at a single instance of time, all these, suppose here are 5, 6, 8 unit. So these 8 unit in a single instance of time work simultaneously. So this is the known as the parallel processing. Now comes to the main topic, that is what is pipeline. First I tell you that is what is the general definitions of pipelining. A pipelining is a technique of decomposing a sequential task into subtasks. All the term is important, with each subtask being executed in a special dedicated stage that operates concurrently with all other stages. Each stage performs partial processing dictated by the way the task is partitioned. The result is obtained from a stage is transferred to the next stage in the pipeline. The final result is obtained after the instruction has passed through all the stages and all the stages are synchronized with a common clock. So what I did? First we check the diagram. This is a basic linear pipeline structure. L is the latches. Latches means between two stages. This is the actually treated as a buffer. And what are the stages? S1, S2 up to Sk are the different stages. Stages means pipeline stages. Now one job is come in your system. So a task, first job is first divide the task into different subtasks, and then each subtask being executed as dedicated stage. Suppose S1 is your addition, S2 is your multiplication, similarly S4 is the logical operation. So different functional unit holds the different stages. So each stage perform partial processing. Partial processing means suppose S1 only operation is the addition. So if in your job addition operation is required, addition is performed, then passes the result to the next stage in the pipeline. Now S2, suppose your addition A plus B is created in the S1 stage and it is passes to the next stage. Now S2 is the logical unit. But your data is not, your job is not required logical operation. Then it again passes to the next stage. So in this way, the one by one each stage is there. Whatever is required in your instruction, as per your instruction, it is working on that stage and passes the temporary or the partial output to the next stages. And the final result is obtained after the instruction has passes through all the stages. That means if one job entered into the pipeline, it passes all the stages, the output passes all the stages, and if there are k number of stages, then after the moving the data through the k stages and final output gets from the last stages. So and it is important, all the stages are synchronized with a common clock, that is operate on a connected with a single clock. So this is the concept of basic linear pipeline. Now take an example. Suppose there are 100 students to perform and perform 5 questions. In an exam, there are 5 questions in the exam paper and 100 students appear in that particular examination. Now calculate the evaluation time for checking the answer script and assume each question evaluate 5 times. So now check, if there are 100 students and 5 questions, each question required 5 minutes, then in a non-pipeline structure, non-pipeline means suppose I am the teacher, I evaluate the one answer script and each question 5 minutes. So 5 into 5, there is 25 minutes to check one paper. So in this way, if 100 students are there, so 100 question answer script, so 100 into 25, that is 2500, 2500 minutes is required to evaluate all the answer script. It is a non-pipeline structure, that is sequential structure. So 5 minutes required one question. There are 5 questions, so simple mathematics, 5 into 5, 25 minutes, and there are 100 students, so 100 exam paper, so 100 into 25, that is 250. Now in pipeline structure, what happens? First, suppose there are 5 evaluators. Evaluators means there are 5 experts, suppose. First, question number 1, expert 1, question number 2, expert 2, in this way 3, 4, 5. Each expert or each evaluator is specialized one particular one questions. Okay, so then what happens? Now question number 1, exam paper 1 comes to evaluator number 1. So if question 1 is matched with its specialization, it evaluated and passes to the next step. In that time, in the next interval, the second paper comes on. Okay, it looks like this. Suppose there are 4 evaluator, S1, S2, S3, S4, S5. The first answer script comes here and it passes the data to the next, and in the meantime the next answer script comes to the S1. If it is required, it checks, otherwise it passes to the next. So in this way, after 5 minutes, or because there are 5 questions, so after evaluating 5 questions, the first answer script is totally 5 into 5, that is 25 minutes. The first answer script evaluated fully. At the next 5 minutes, the second one comes. Third 5 minutes, the third question answer script comes. So in this way, if we calculated in a pipeline structure, what is the time required? First question, first answer script, it is the 25 minutes, and after that, after every 5 minutes, the next answer script is evaluated. So there are 100 minus 1, 99 answer script is there, and total time for 5. So 99 into 5 added with 25, that is the 520 minutes. Now you check the comparison, that is 2500 minutes and 520. Which one is the minimum? Pipeline structure gives you the minimum time, that is it gives you the better output. So this is the concept of pipeline structure. So a linear pipeline can process a succession of subtasks with a linear precedence graph. This is actually known as the linear precedence graph. With a linear precedence relation, task T of j cannot start until the earlier subtask Ti. If I is the earlier task and j is the next task, so earlier task end, then your next task will start. And overlap operation of pipeline process shown in the space-time diagram. This is the space-time diagram also. This is the overlapping. If there are overlapping, we can check easily there is any overlapping or not. In this diagram, no overlapping. Now, how to calculate the clock period? These are some parameters to calculate the pipeline efficiency. What is clock period? The logic circuitry in each stage Si has a time delay denoted by if tau I, and let tau I be the time delay of each interface latch. Latch means the buffer where you store the data. The clock period of a linear pipeline defined by tau I tau, final tau equals to tau I equals to I equals to 1 to k plus tau 1, where tau of m is the maximum time delay. The reciprocal of the clock period is called the frequency of the pipeline, f equals to 1 by tau. Now how to calculate the performance? The three parameters to calculate the performance of the pipeline process: speed up, efficiency and throughput. What is speed up? The formula to calculate the speed up is S of k equals to time to execute n number of tasks in k stage non-pipeline divided by time to execute n tasks in k stage pipeline. So non-pipeline divided by pipeline processor time. So in non-pipeline structure, if there are number of k stage and n tasks, so n into k, and in pipeline structure k plus n minus 1. If that maximum speed up is equals to k, that is sk equals to, we reach k if n is very much greater than 2k. N means a task, if compared to the k, that is the number of stages, if n is very much high, then the maximum speed up we achieved is equivalent to number of stages. But maximum speed up is never fully achievable because the data dependency between the instruction, interrupts and different program branches. Fully not achievable, 100% is not achievable, but it reached to maximum speed up. Now efficiency. To define the efficiency, we defined another term, time space span. It is the product area of a time interval and a state space in the space-time diagram. A given time space span can be either a busy state or a idle state, but not both. That is, from the time space diagram, we can determine that the state is busy or idle. Now what is efficiency? The efficiency of a linear pipeline is measured by the percentage of busy time space spans over the total time space span, which equals the sum of all busy and idle. That is, the total time is busy and idle time is the total time, and you can calculate the percentage of busy time space span. So n k tau be the number of tasks, number of stages and the clock period of a linear pipeline. Then the formula to calculate the efficiency is eta equals to n k tau, again non-pipeline by pipeline, n k tau divided by k into tau plus n minus 1 into tau. The equals to, it is, if we simplify, n by k plus n minus 1. If eta tends to 1, as when n equals to infinite. Again n is the number of tasks. So if number of tasks is huge or larger, very much larger, then we give the better efficiency. So pipeline means when the number of tasks is high, then we get the better results. Finally, the throughput, the number of tasks that can be completed by a pipeline per unit time is called its throughput. So mathematically it is defined by omega, that is the n by k into tau plus n minus 1 into tau, it is eta by tau. So again, what is the ideal case? Omega equals to 1 by tau, that is the frequency when eta tends to 1. That means maximum throughput of a linear pipeline is equal to its frequency. Now some numerical problems I discuss with you. So there are time delays for 4 stages. Suppose there are 4 stages, tau 1 equals to 60 nanosecond, tau 2 50, tau 3 90, tau 4 80. And the latch delay equals to tau 1 equals to 10 nanoseconds. So the question, very simple question, what would be the how to calculate the maximum clock frequency of the above pipeline and what is the speed up of the pipeline over the non-pipeline. So the first question is calculate the clock period. First how to calculate the frequency. Frequency means the reciprocal or reverse of the clock period. So clock period equals to tau equals to 90, means the maximum time delay what is 60, 50, 90 and 80. So maximum is 90, and with the addition with the latch delay 90 plus 10 equals to 100 nanosecond, and clock frequency equals to f equals to 1 by tau equals to 1 by 100 equals to 10 megahertz. Frequency unit is hertz, so 1 by 100 megahertz. Now what is the maximum speed up? So if we perform this above problem in non-pipeline structure, equals to tau 1 plus tau 2 plus tau 3 plus tau 4, that is a 280 nanosecond. So comparison, that is speed up, 280 divided by what is the clock weight? 100. For pipeline it is 100. So 280 divided by 100 equals to 2.8. It is the maximum speed up. Now another question. Consider a pipeline having 4 phases with a duration 60, 50, 90 and 89. Given the last date 10. Now calculate, there are again 5 to 6 questions. What is the pipeline cycle time? What is non-pipeline execution time? Speed up ratio, pipeline time for 1,000 tasks, sequential time for 1,000 tasks, and finally the throughput. These are the 6 questions. So there are 4 stage pipeline is used. Delay the stages 60 plus 50, 60, 50, 90 and 80, and last delay is for each register is 10 nanoseconds. So the first question is pipeline cycle time. How to calculate the cycle time? Maximum delay due to any stage plus delay due to register. So max of 60, 50, 90, 80 equals to 90 plus 100 nanoseconds. So the first question answer is pipeline cycle time. Part 2 question is non-pipeline execution time. Non-pipeline execution time is just direct addition 60 plus 50, 90 plus 80 to 89. Speed up non-pipeline execution time divided by pipeline execution time. So 280 divided by 100. Because pipeline time is 100 and non-pipeline time is 280. The 280 divided by 100, 2.8. Now pipeline time for 1000 tasks. So pipeline time for 1000 tasks is time taken for the first task plus time taken remaining 1000 minus 1999 tasks. So 1 into 4 clock cycle plus 99 into 1 clock cycle. So 4 into cycle time, what is the first cycle time? It is 100. So 4 into 100 because there are 4 stages. So 4 into 100 plus 999 into 100. So time is 400 plus 99900, that is 1,300,000 nanoseconds. So this is the pipeline time for 1000 tasks. And for sequential time, just multiply with 1000 tasks with time taken for 1 task. So 1000 into 280. So 2,80,000. So just check the difference. So here 1,300,000 nanosecond, here 2,80,000. So throughput is for pipeline execution 1000 tasks, number of instruction executed per unit time, that is the throughut for that pipeline execution time. 1000 tasks by divided by this one. Now the next important part is classification of pipeline processor. What are the different types of pipeline? So according to the level of processing, Handler, that is in 1977, one scientist has proposed the following classification: arithmetic pipeline, instruction pipeline and the processor pipeline. So first the arithmetic pipeline. The ALU of the computer can be segmented for pipeline operations in various data formats. So we know ALU performs all the arithmetic and logical operations. So there are arithmetic unit means all the addition, subtraction, multiplication, division, increment, decrement, all are arithmetical operations. So in the pipeline structure, these are the name of actually the pipeline structure, that is the 4-stage pipeline, star 100, 8-stage pipeline used in TISC. These are the name of this. Next, the instruction pipeline. The execution of a stream of instruction can be pipelined by overlapping the current instruction with fetch, decode, operand and subsequent instructions. So these are the main operations when we perform any instruction execution. So instruction execution stage, all of you know, that is the fetch, then decode, then operand fetch, the execution and store back. So fetch means the memory operation, decode means the data converted to machine language, and operand fetch means again one memory operation where the operand is there. So all the high performance computer are now equipped with a pipeline. So that means all these fetching, decoding, operand fetching are come to a pipeline, then one by one instruction use this. Suppose first operation, first instruction use the fetch, operator fetch or instruction fetch. Then it passes to the decoder or decode stage. Then in the meantime, at that cycle time, the next instruction comes to the fetch operation. And then after third cycle, the first operation goes to operand fetch, second operation goes to decode stage, and third operation comes to into the pipeline, that is the operator fetch. So in this way, in a pipeline manner, the instruction is executed. And the processor pipeline, it is the same processor pipelining of the same data stream by cascading the processor, each of which processes by specific task. Here different one processor is designed in this way, that is a particular task is performed, but here no practical use of this. And according to the pipeline configuration and control strategy, Ramamurthy and Lin in 1997 also proposed another classification, that is the unifunction or multifunctional pipeline, static and dynamic pipeline, and scalar or vector pipeline. So by definition, unifunction and multifunction, from the name you understand, a pipeline unit with a fixed and dedicated function is the unifunction, there is only one functional there. And multifunction pipeline may perform different functions, either different times or at the same time, by interconnecting the different stages. In multifunctional, they are internally connected. Now, static versus dynamic pipeline. A static pipeline may assume only one functional configuration at a time. Static means it is no running procedure. Static means it is predefined and only functional configuration at a time. The static pipeline can be either unifunctional or multiple, but it is predefined. But in a dynamic pipeline structure, it permits several functional configurations exist simultaneously. In this sense, a dynamic pipeline must be multifunctional. That is addition, in subtraction, multiplication, logical in this way. So on the other hand, the unifunctional piping must be static. Generally unifunctional, that is if it is single operation, it is static, and multifunctional is the dynamic. And last one is the scalar and vector. A scalar pipeline processes a sequence of scalar operands under the control of a do loop. Vector pipeline processes vector instruction over vector operands. So there are different operands. Scalar operands, scalar means a single data, vector means looks like a array structure, multiple data. So scalar operands under the control of a do loop, and vector pipeline is very vector operands. Now here comes to end. I give you through this slide the basic overview of the pipeline. What is pipeline? Before pipeline, what is parallel processing? After that, what is the basic overview of linear pipeline structure? What are the different stages? What are the concept of pipeline? Some numerical problems shared with you, and different parameters or performance to gain the performance of the pipeline processor, and some numerical problems along with the classification of the pipeline processor. So thank you. Hope you enjoy the slides. Thank you.